In the silent depths of space, far from the warmth of any nearby sun, lie vast clouds of gas and dust adrift between the stars. These immense structures, called molecular clouds, are the raw material of stellar creation. They span light years in every direction, cold and dark, composed mostly of molecular hydrogen, helium, and traces of heavier elements forged in earlier generations of stars. At first glance, they seem tranquil, motionless, and eternal. But hidden within them are slow currents of energy and matter that will, over millions of years, give rise to new suns. Astronomers study these nurseries using radio telescopes and infrared observatories, instruments sensitive to the faint glow of cold molecules and dust. Visible light cannot easily escape these regions, for their densities, though thin by earthly standards, are sufficient to absorb and scatter photons. The James Webb Space Telescope has revealed, in exquisite detail, the intricate structure of these clouds, filaments twisting through the darkness, knots of denser gas, and small pockets where gravity has begun to take hold. Each knot, each quiet pocket, may be the seed of a future star. Within a molecular cloud, slight variations in density can become amplified. A region only marginally denser than its surroundings experiences a slightly stronger pull of gravity, drawing in more material. As mass accumulates, the pull grows stronger still, leading to runaway collapse. This process, known as gravitational instability, is described mathematically by the Jeans criterion, named for the British physicist James Jeans. If the mass of a gas region exceeds a certain limit, gravity overwhelms internal pressure, and collapse begins. The boundary between stability and collapse depends on temperature, density, and the composition of the gas. In the coldest and densest regions, temperatures around 10 Kelvin and densities of hundreds of molecules per cubic centimeter, collapse becomes inevitable. As the cloud fragment collapses, it cannot do so uniformly. Random motions, magnetic fields, and turbulence shape the flow of gas, forming elongated filaments and rotating clumps. Observations from the Atacama Large Millimeter, Submillimeter Array, or ALMA, show that these filaments are common structures across star-forming regions like the Orion Molecular Cloud and the Taurus Complex. They are not merely transient patterns of dust, they are the scaffolding from which new stellar systems arise. Along these filaments, gravity gathers material into denser cores, each perhaps only a fraction of a light-year across, containing enough mass to form one or several stars. Inside these cores, as collapse proceeds, the material falls inward toward a central point. Potential energy converts into kinetic and thermal energy, heating the gas. At first, radiation escapes easily, allowing the core to cool and collapse further. But as density rises, radiation becomes trapped, and the temperature slowly increases. The object that forms at the center is called a protostar. It is not yet a true star, for nuclear fusion has not begun, but it is already a distinct entity, a sphere of hot gas, opaque to radiation, surrounded by an envelope of infalling material. The protostar phase is one of transformation. Angular momentum, a fundamental property of any rotating system, prevents all material from falling directly onto the core. Instead, gas settles into a disk around the forming star, flattening as it orbits. This circumstellar disk is a natural consequence of rotation and conservation laws. Within the disk, complex processes occur. Gas spirals inward, dust grains collide and stick together, and magnetic fields drive powerful outflows. Jets of plasma emerge from the poles of the protostar, shooting outward at hundreds of kilometers per second. These outflows, visible in optical and infrared images as Herbig-Haro objects, clear away surrounding gas and regulate the rate at which the young star accretes mass. The interplay between gravity, pressure, and angular momentum creates a delicate balance. If accretion continues too rapidly, the star can grow massive enough to ignite fusion prematurely, halting further growth. If accretion ceases too soon, the star remains small, perhaps destined to become a red dwarf. Observations suggest that most stars form in groups or clusters, not in isolation. Within a single molecular cloud, dozens or hundreds of protostars may form simultaneously, their gravity influencing one another. Over time, the densest regions may give birth to high-mass stars, whose powerful radiation and winds will reshape the surrounding cloud. In star-forming regions like the Pillars of Creation in the Eagle Nebula, this cycle is vividly on display. The towering columns of gas photographed by Hubble and revisited by JWST are being slowly eroded by the ultraviolet light from nearby massive stars. Yet within the tips of those columns, new protostars are emerging, their formation triggered by the very radiation that will eventually disperse their birthplace. Star formation is thus both creative and destructive, a process that feeds on the remnants of previous generations, constantly renewing the cosmic landscape. Temperature and pressure play crucial roles in the early stages. The collapse of a cloud core can be described by the equations of hydrodynamics, modified by radiation transport and magnetic fields. As the core contracts, its temperature rises from a few tens of Kelvin to several thousand. When the central temperature reaches about 2000 Kelvin, hydrogen molecules begin to dissociate, absorbing energy and temporarily slowing the collapse. Once dissociation is complete, the core resumes contracting until electron degeneracy pressure becomes significant, forming a hydrostatic object. At this stage, called the first hydrostatic core, the protostar's interior becomes increasingly opaque, trapping heat and stabilizing the collapse for a time. Further contraction leads to the second hydrostatic core, a denser and hotter region where temperatures exceed 100,000 Kelvin. Eventually, when the core temperature surpasses about 10 million Kelvin, nuclear fusion ignites. The first fusion reactions involve deuterium, a heavy isotope of hydrogen, which burns at lower temperatures than ordinary hydrogen. Deuterium burning provides a brief but important phase of stability, allowing the young star to adjust its structure. Only later does hydrogen fusion begin through the proton-proton chain, marking the birth of a true main sequence star. Different stars follow different evolutionary paths depending on their initial mass. Low-mass protostars contract slowly, taking tens of millions of years to reach the main sequence. High-mass protostars evolve much more quickly. Their intense radiation pressure drives strong winds that disperse their natal envelopes even before fusion is fully established. ALMA and JWST observations of regions like the Carina Nebula reveal the presence of massive protostellar objects, each dozens of times the Sun's mass, forming within dense cocoons of dust. These massive stars will have short but brilliant lives, ending in supernovae that enrich the interstellar medium with heavy elements. Star formation efficiency, the fraction of a cloud's mass that becomes stars, is typically low. Most of the gas in a molecular cloud is dispersed by feedback from young stars, radiation pressure, stellar winds, and supernova explosions. Yet the small fraction that does condense into stars is enough to maintain the galaxy's luminosity and chemical evolution. The Milky Way converts roughly 1 to 2 solar masses of gas into stars each year, a gentle but persistent rhythm that has continued for billions of years. The process is not uniform across the galaxy. Spiral arms serve as sites of active star formation, where density waves compress gas and trigger collapse. In contrast, the interarm regions are relatively quiescent. The galactic center hosts intense bursts of star formation, fueled by infalling gas and strong gravitational forces. Even dwarf galaxies, with their shallow gravitational wells, experience episodes of star formation driven by interactions and mergers. Star formation thus shapes galaxies on both local and cosmic scales, linking the life cycles of stars to the evolution of the universe itself. As we observe more deeply with instruments like JWST, we are beginning to see star formation occurring in distant galaxies, billions of light-years away, during the early epochs of the cosmos. These ancient stars formed under conditions quite different from those in the Milky Way today. The early universe contained less heavy elements, and cooling mechanisms were limited. The first generation of stars, known as Population 3, likely formed from pristine hydrogen and helium. Simulations suggest they were extraordinarily massive, perhaps hundreds of times the Sun's mass, and their brief lifetimes seeded the cosmos with the first heavy elements. Every stage of star formation, from the collapse of a cold cloud to the ignition of nuclear fusion, unfolds on timescales far longer than any human life. Yet through the patience of observation and the ingenuity of physics, we can reconstruct the process as though we were watching it unfold in slow motion. The tranquil darkness of molecular clouds, the subtle glow of protostellar disks, the flickering birth of light from fusion, all are chapters in a cosmic story that continues endlessly. When we gaze upon a region like the Orion Nebula, we are seeing this story mid-sentence. Thousands of young stars populate its glowing interior, surrounded by arcs of gas and pillars of dust. Infrared images reveal countless hidden objects still wrapped in their birth cocoons. Each will eventually emerge as a new star, perhaps with planets, perhaps with worlds yet to form. The radiation from these newborn suns illuminates the surrounding gas, creating the diffuse glow we see through telescopes. In that light lies the memory of collapse, heat, and ignition, the quiet transformation of darkness into radiance. The physical understanding of these processes comes from a combination of observation, theory, and simulation. Astronomers build computer models that track the evolution of gas clouds under the influence of gravity, magnetic fields, and turbulence. These models, run on powerful supercomputers, reproduce the filamentary structures and clustered formation observed in real clouds. They reveal that turbulence, rather than being a mere complication, may be essential to star formation. It stirs the gas, preventing premature collapse on large scales while promoting local density enhancements where stars can form. In addition to turbulence, cosmic magnetic fields shape the dynamics of clouds. Though weak by terrestrial standards, these fields thread through interstellar space, guiding charged particles and influencing the flow of gas. Observations using polarized light and radio emission have shown that magnetic fields can channel material into filaments and slow the rate of collapse. Yet they are not strong enough to prevent star formation entirely. Instead, they act as moderators, stretching the timescales and introducing complex patterns of rotation and outflow. Star formation also depends on chemistry. Within molecular clouds, atoms combine to form molecules on the surfaces of dust grains. These grains, tiny silicate or carbon particles less than a micron in size, act as catalysts. Hydrogen atoms stick to their surfaces, meet, and bond to form molecular hydrogen. Other elements, oxygen, nitrogen, carbon, participate in reactions that produce water, ammonia, carbon monoxide, and a variety of organic compounds. These molecules are not only tracers for astronomers, they play a physical role by radiating energy away and cooling the gas. Without molecular cooling, the clouds would remain too warm for collapse to proceed efficiently. As JWST peers into these regions with unprecedented resolution, it detects the spectral fingerprints of such molecules, confirming long-standing theories and revealing new complexities. In some protostellar disks, evidence of complex organic chemistry, precursors to amino acids and other building blocks of life, has already been found. Though this belongs to the later stages of star and planet formation, it reminds us that the birth of stars and the origins of potential life are part of the same continuum of cosmic evolution. From a distance, a star-forming region may appear chaotic. Tangled filaments, bright knots, dark shadows, jets and outflows crossing one another. But when viewed as a system governed by physics, a deep order emerges. Each phenomenon arises naturally from the equations that describe fluid motion, radiation, and gravity. The apparent complexity is the beauty of self-organization in nature. From simplicity, hydrogen and helium, arises the immense diversity of stars, planets, and, eventually, life itself. Star formation does not occur in isolation but is embedded in the galactic environment. Supernova explosions from earlier generations of stars sweep through space, compressing nearby clouds and triggering new waves of collapse. This process, called triggered star formation, links the death of stars to the birth of others. Observations of shells and bubbles in the interstellar medium show how energy from massive stars propagates outward, sculpting the next generation of stellar nurseries. In this way, galaxies sustain a continuous cycle of creation and renewal. When astronomers map the Milky Way in radio wavelengths, they can trace the locations of giant molecular clouds, spiral arms, and star-forming complexes. These maps reveal that our galaxy is not uniform but a living structure, its gas and dust circulating through regions of birth and decay. Even within a single cloud, star formation may proceed in bursts, separated by quiet intervals as feedback reshapes the environment. Over cosmic time, this ebb and flow determines the distribution of stellar populations and the evolution of the galactic disk. At the heart of all these processes lies the same universal law: gravity drawing matter together, transforming potential energy into light. The formation of a star is gravity's most elegant expression, a balance between collapse and resistance, between compression and radiation. Each new star is an equilibrium point achieved after millions of years of adjustment, a glowing sphere that will remain stable for billions more. To imagine these events on human timescales is impossible, yet by compressing them into words and visuals, we bring them within the reach of perception. The soft glow of a nebula, the faint hum of radio waves from molecular gas, the shimmering edge of a protostellar disk, all become whispers in a cosmic lullaby. The science behind them is precise, mathematical, and testable, yet the effect is profoundly soothing. The realization that creation is an ongoing process, vast and patient, happening all around us. As we reach the end of this first section, the scene is set. A cold, dark cloud in the interstellar medium. Subtle disturbances beginning to form. Gravity quietly taking hold. Within this stillness, invisible yet inevitable, lie the beginnings of light. The path ahead will follow the journey of that light as it grows stronger, from protostar to main sequence, from the calm of collapse to the radiance of a newborn sun. The dense heart of a collapsing cloud, once diffuse and formless, begins to take on structure and identity. Within its depths, the infalling gas grows warmer, and faint light emerges from the compression of matter. Though that light cannot yet escape the surrounding envelope of dust, it signals the quiet beginning of a new star's long evolution. The protostar, cradled in its cocoon, is still hidden from optical view, but in infrared wavelengths it begins to glow faintly, marking the transition from a dark condensation to a luminous embryo of fusion. The protostar's structure is not yet stable. It is a sphere of gas supported partly by internal pressure, partly by the constant infall of material from its surrounding disk. Energy flows outward, carried by convection and radiation, yet gravity continues to draw more matter inward. This delicate interplay determines the rate at which the star gains mass. The luminosity that escapes the surface of the protostar is due not to fusion but to the conversion of gravitational potential energy into heat and radiation. Every atom falling inward releases a tiny amount of energy upon joining the star, and over millions of years these small increments add up to a steady glow. The disk surrounding the young star is a dynamic structure. Its inner regions, heated by radiation and friction, glow in infrared light, while the outer regions remain cool and dusty. Within it, material moves in nearly Keplerian orbits, each particle following a path determined by the central mass. Viscosity within the disk causes gas to spiral slowly inward, transferring angular momentum outward. This process, though invisible to the eye, governs the star's growth and sets the stage for later planetary formation. Observations from ALMA have revealed striking images of these disks, showing gaps and rings sculpted by emerging structures and the gravitational influence of the forming star. Jets and outflows continue to stream from the poles of the protostar, acting as pressure valves that carry away excess angular momentum. These narrow, collimated flows extend for light years, carving channels through the surrounding cloud. They are powered by magnetic fields anchored in the disk, where rotating plasma interacts with field lines and accelerates material outward. The result is a balanced exchange. As mass accretes onto the star, momentum escapes through the jets, allowing the core to contract further without spinning apart. In optical images, these flows appear as shimmering filaments against the darkness, illuminated where they strike nearby gas and cause it to glow. Inside the protostar, temperatures rise steadily. At a few thousand Kelvin, the outer layers are convective, transporting heat outward through the slow motion of gas. Deeper within, pressure and density increase to levels beyond direct experiment, but theory and models describe their evolution with precision. When the central temperature reaches around 1,000,000 Kelvin, deuterium fusion begins. This process, deuterium burning, does not release vast amounts of energy but is sufficient to stabilize the core temporarily. It slows contraction, allowing the protostar to radiate away heat and adjust its internal structure. For a brief epoch, the young star hovers in this intermediate state, not yet on the main sequence but no longer collapsing freely. Here, the energy from deuterium burning helps to inflate the outer layers of the protostar, creating a large, luminous object with a relatively cool surface. Such young stars emit most of their light in the infrared, and their brightness can vary as accretion fluctuates. Some undergo episodic outbursts known as Fu Orionis events, named after one of the first observed examples. During these events, the accretion rate increases dramatically, causing the luminosity to rise by orders of magnitude. The outburst may last for decades or centuries before fading, leaving behind signs of turbulence in the disk. These variations, seen in many young stellar objects, suggest that star formation is not a smooth process but one punctuated by bursts of growth. As the protostar gains mass and its core continues to heat, hydrogen fusion eventually begins through the proton-proton chain. The onset of hydrogen burning marks the moment when the star achieves hydrostatic equilibrium. Inward gravitational forces are balanced by outward pressure from fusion energy. The protostar becomes a main sequence star, stable and self-sustaining. The dusty envelope dissipates, blown away by stellar winds and radiation, and the surrounding disk begins to evolve into the remnants from which planets may form. What was once hidden within a molecular cloud now shines freely into space, contributing its light to the galaxy's tapestry. For stars like the Sun, this process takes about 50 million years from initial collapse to main sequence stability. For smaller stars, the journey is longer. For massive ones, much shorter. The differences arise from how energy and pressure interact within the contracting core. Massive protostars reach the required temperatures quickly, igniting fusion while still accreting material. Their intense radiation pressure then halts further growth, dispersing the envelope. In contrast, low-mass protostars evolve slowly and gently, often forming in clusters where gravitational interactions influence their development. The physics of this transformation can be visualized in the Hertzsprung-Russell diagram, a plot of luminosity versus temperature. Protostars follow a nearly vertical path downward on this diagram, known as the Hayashi track. During this phase, their luminosity decreases as they contract, but their temperature remains relatively constant. Eventually, as they approach the main sequence, they move horizontally along the Henry track, becoming hotter and less luminous until equilibrium is reached. These theoretical tracks, developed through stellar evolution models, provide a framework for interpreting observations of young clusters where stars are caught in various stages of formation. In regions like the Taurus-Auriga complex or the Orion Nebula cluster, astronomers have catalogued hundreds of young stars at different points along these paths. By comparing their luminosities and temperatures, scientists can estimate their ages and masses. Such studies reveal that star formation within a single cloud can occur over several million years, producing a population of stars with a range of properties. The diversity seen in these clusters, some stars still embedded in dust, others already shining openly, illustrates the continuum of stellar birth. While gravitational collapse and nuclear physics explain much of star formation, feedback processes are equally important in shaping outcomes. The radiation from newly formed stars heats nearby gas, raising its pressure and halting further collapse. Stellar winds and outflows sweep away material, limiting the available mass. In regions with massive stars, ionizing radiation creates expanding bubbles of plasma that erode molecular clouds. This feedback not only ends star formation locally but can also trigger it elsewhere by compressing nearby gas. The result is a complex, self-regulating system where creation and inhibition occur side by side. Advances in observation technology have allowed astronomers to study these mechanisms in unprecedented detail. The James Webb Space Telescope's infrared sensitivity penetrates dusty regions that were once opaque, revealing embedded protostars and disks with remarkable clarity. ALMA's high-resolution imaging of millimeter wave emission traces the structure of cold gas and dust, showing how filaments feed material into forming stars. Together, these instruments provide a complete picture of the birth process, from the earliest collapse to the moment fusion begins. Recent JWST data from the Orion Nebula and the Perseus molecular cloud show that even small variations in local conditions, such as magnetic field strength or turbulence intensity, can dramatically affect star formation rates. Some filaments host rapid, clustered formation, while others remain dormant for long periods. This suggests that the efficiency of star formation is governed not by simple global parameters but by the intricate balance of forces within each region. Models incorporating these details reproduce the observed diversity, emphasizing that no two stars share the exact same origin story. As the protostar reaches stability, the surrounding disk becomes a crucible of evolution. Dust grains within the disk collide and adhere, forming aggregates that grow from micrometers to millimeters and eventually to kilometer-sized planetesimals. While this process leads toward planet formation, it also influences the star itself. As material accretes inward, it carries angular momentum and magnetic flux that can modulate the star's rotation rate. Some young stars spin rapidly, completing a rotation in less than a day, while others slow as magnetic interactions with the disk remove angular momentum. Over time, these effects determine the star's magnetic activity, its wind, and its eventual habitability potential for future planets. The transition from protostar to main sequence star is gradual, not a sudden ignition. The fusion reactions start in the core and slowly increase in strength until they dominate the energy budget. The luminosity becomes steady, the radius stabilizes, and the surface temperature reaches the value characteristic of its mass. For a star like the Sun, this means a temperature of about 5,800 Kelvin, a delicate equilibrium that will endure for billions of years. The winds that once sculpted the surrounding nebula now fade, leaving behind a clear region of interstellar space illuminated by new light. Observing young stars provides a glimpse into the earliest phases of stellar life. Astronomers use spectroscopic techniques to measure their compositions and velocities, revealing how they accrete mass and interact with their disks. Polarimetric observations trace magnetic fields, showing the complex geometry of inflow and outflow. Time domain studies, monitoring brightness variations over weeks or months, uncover the dynamic nature of accretion and rotation. Each data set adds a layer to the story, confirming that star formation is not a uniform process but a tapestry of diverse and evolving phenomena. The broader cosmic context of these events extends beyond individual clouds. Galaxies themselves evolve through star formation, converting gas into light and recycling material through feedback. In starburst galaxies, the process occurs at extraordinary rates, hundreds or thousands of solar masses per year, driven by interactions and mergers. In contrast, older, quiescent galaxies show declining activity as their gas reservoirs are depleted. The study of star formation thus connects the microscopic physics of gas and dust to the macroscopic evolution of galaxies over billions of years. As we contemplate this immense scale, it becomes clear that every star in the night sky shares a common origin: collapse, heating, ignition. Each carries the signature of the same physical laws, yet each follows a unique path shaped by its environment. The delicate balance of forces that govern these transformations reflects a universal harmony, one that persists across the universe. In this sense, to study star formation is to glimpse the creative rhythm of nature itself, a slow unfolding of order from the quiet chaos of interstellar clouds. If we could accelerate time, we would see the clouds' slow drift resolve into motion. We would watch filaments converge, knots brighten, disks form and flatten, and jets erupt like brief flashes in the dark. But in reality, these changes occur over spans so long that they become imperceptible to direct observation. Only by assembling snapshots from countless regions across the sky can we reconstruct the full sequence. In doing so, we bridge the gap between human perception and cosmic time, allowing ourselves to witness creation in slow motion. Eventually, the surrounding molecular cloud disperses completely. The newborn star, now freed from its cocoon, joins the open cluster of its siblings. Over tens of millions of years, the cluster will expand, and its members will drift apart, each following its own orbit around the galactic center. Some will remain bound in multiple systems, others will wander alone. The star has entered the longest and most stable phase of its existence, shining quietly as hydrogen fuses into helium deep within its core. In this quiet stability lies the essence of stellar life: balance. A continuous exchange between gravity's inward pull and radiation's outward push sustains the star in equilibrium. The same forces that shaped its birth now maintain its steady glow. The complexity of the preceding stages gives way to simplicity: a luminous sphere radiating energy into space, a beacon in the dark. The calm after the storm of creation. As we reach the end of this section, the protostar has completed its transformation. What began as a cold fragment of a cloud has become a shining star, the result of gravity, pressure, and time. Around it, the remnants of its disk linger, some of which may one day coalesce into planets, moons, and comets. The story of star formation now expands beyond the individual object, reaching into the collective processes that shape entire clusters and galaxies. In the next chapter, we drift outward, exploring how these newborn stars interact with their surroundings, how their light sculpts the gas around them, and how the cycle of stellar creation continues without end. The newborn star does not emerge into solitude. Around it, other stars are taking shape within the same cloud, each at a slightly different stage of evolution. Together, they form a cluster, a loose family bound by the common origin of a shared molecular womb. In the cold light of infrared images, such clusters appear as constellations in embryo, their members still shrouded in veils of dust. Over time, as their winds and radiation clear the surrounding gas, the stars become visible, revealing the intricate tapestry of a stellar nursery. The formation of clusters is a natural outcome of the way gravity acts on turbulent clouds. When a giant molecular cloud fragments, it rarely produces a single star. Rather, it collapses in multiple locations simultaneously, forming dozens or hundreds of protostars. The interactions among these forming objects, their mutual gravitation, their outflows, their radiation, create an environment of complex feedback. Some protostars may merge, others may be ejected from the cluster before fully forming. The resulting diversity of masses and separations gives rise to the initial mass function, a statistical distribution that describes how many stars of each mass a cloud produces. The initial mass function, or IMF, is one of the most fundamental empirical laws in astrophysics. It reveals that most stars formed are of low mass, small, faint, and long-lived. Massive stars are rare, but they dominate the luminosity and feedback of their environments. The IMF appears to be remarkably similar across different galaxies and epochs, suggesting that star formation follows universal principles. Yet, recent observations with JWST hint at subtle variations, especially in regions with low metallicity, where cooling processes differ. Understanding these variations helps astronomers trace the evolution of galaxies across cosmic time. Within a cluster, the gravitational potential is deep enough that stars interact dynamically. Close encounters can alter their trajectories, forming binary and multiple systems or ejecting low-mass members entirely. Simulations show that most stars are born in binaries or higher-order systems, a fact confirmed by observations of young clusters like the trapezium in Orion. These interactions influence the architecture of future planetary systems, as gravitational perturbations in the early stages can affect disk orientations and planet formation. Thus, even in its infancy, a star's future environment is shaped by the company it keeps. The radiation from massive young stars exerts a profound influence on the surrounding medium. Ultraviolet photons ionize hydrogen, creating expanding bubbles of plasma known as H2 regions. The boundaries of these regions glow with recombination light, producing the colorful emission nebulae that adorn astrophotography. Yet behind this beauty lies energetic feedback. The ionization front drives a shock wave into the neutral gas, compressing it and sometimes triggering new rounds of star formation in adjacent regions. This process, called sequential or triggered star formation, ensures that the energy released by one generation of stars contributes to the birth of the next. As clusters mature, their most massive members evolve rapidly. O-type stars, burning hydrogen at extreme rates, live only a few million years before ending their lives as supernovae. When they explode, they release vast amounts of energy, dispersing the remaining gas and dust. The cluster, once wrapped in its natal cloud, becomes exposed to the galaxy. Some of its stars remain bound, forming an open cluster that may persist for hundreds of millions of years. Others drift apart, populating the galactic disk. The material expelled by supernovae enriches the interstellar medium with heavy elements, oxygen, carbon, iron, that will become part of future stars and planets. In this way, each generation builds upon the ashes of the last. The chemistry of the interstellar medium thus evolves continually. Early in the universe, before heavy elements existed, star formation relied on molecular hydrogen as the primary coolant. Today, elements like carbon and oxygen provide additional cooling through fine structure line emission, allowing clouds to fragment more efficiently and produce smaller stars. Dust grains, composed of silicates, graphite, and ices, also play a crucial role by shielding gas from radiation and serving as surfaces for molecule formation. Observations of dust emission at sub-millimeter wavelengths allow astronomers to estimate the mass and temperature of star-forming clouds, linking the microphysics of grains to the macroscopic process of star birth. Across the Milky Way, star formation follows patterns shaped by the galaxy's spiral structure. The spiral arms are not rigid objects but density waves, regions of enhanced mass density that move through the disk. As gas enters a spiral arm, it slows and compresses, triggering cloud formation and collapse. When it leaves the arm, the newly formed stars drift ahead, creating a sequence of evolutionary stages that can be traced in maps of star-forming traces like carbon monoxide and H-alpha emission. This spiral density wave theory, developed in the mid-20th century, explains why young stars and clusters are concentrated along the arms, illuminating the galaxy's spiral pattern. Yet star formation is not uniform even within these arms. Observations show that it often occurs in giant complexes, tens to hundreds of parsecs across, containing multiple generations of stars. These complexes evolve as coherent structures, their internal dynamics governed by gravity and feedback. Over time, they may disperse or merge with others, contributing to the continuous renewal of the galactic disk. The interplay between large-scale dynamics and local physics creates the fractal texture of star formation, patterns repeating from the scale of individual stars to entire galaxies. Beyond the Milky Way, JWST and ALMA have opened windows into star formation in distant galaxies. By observing at infrared and millimeter wavelengths, astronomers can detect the cold dust and gas that fuel the process, even in galaxies billions of light-years away. These observations show that the basic mechanisms are the same: gravitational collapse, disk accretion, feedback, but the rates and efficiencies vary. In starburst galaxies, the conditions are extreme. Gas densities are higher, turbulence is stronger, and star formation proceeds at a furious pace. Such galaxies, often triggered by mergers, convert their gas into stars much more rapidly than quiescent spirals, illustrating the range of environments in which stars can form. In the early universe, during the epoch known as cosmic noon about 10 billion years ago, star formation reached its peak. Galaxies then were rich in gas and collided frequently, igniting waves of stellar birth that shaped their subsequent evolution. Observations of galaxies from that era reveal clumpy structures and intense emission from ionized gas, signatures of rapid formation. As the universe aged and gas supplies dwindled, star formation slowed, leading to the calmer conditions we observe today. The history of the cosmos, in this sense, is a story of gradually cooling and settling, from a time of brilliant youth to a mature, quieter phase. The mechanisms driving this long-term decline are complex. Galactic winds, powered by supernovae and active black holes, expel gas into intergalactic space, reducing the available fuel. Meanwhile, gravitational heating from structure formation raises temperatures, making it harder for gas to cool and condense. Yet star formation has not ceased. It continues wherever conditions allow, in dwarf galaxies, spiral arms, and even in the outskirts of massive ellipticals. The persistence of this process ensures that new stars and new planetary systems continue to appear throughout the observable universe. Within clusters, the distribution of stellar masses influences their evolution. Massive stars dominate the radiation output but die quickly. Low-mass stars, though faint, live for trillions of years. Over time, gravitational interactions cause clusters to lose mass as stars escape. The remaining system becomes more compact until tidal forces from the galaxy eventually disperse it. The debris of dissolved clusters contributes to the field star population, the countless solitary suns scattered across the disk. Our own Sun likely formed in such a cluster more than 4.5 billion years ago, its siblings now long dispersed. The study of stellar kinematics and chemical composition offers clues to these ancient associations. By measuring elemental abundances and motion, astronomers can identify stars that originated from the same cloud. This field, called galactic archaeology, reconstructs the history of star formation in the Milky Way. It shows that our galaxy has experienced waves of activity, correlated with interactions and accretion of smaller galaxies. Each wave leaves a distinct imprint in the ages and metallicities of stars. In this way, the lives of individual stars become markers of cosmic history, their compositions serving as fossils of past events. On larger scales, entire galaxies interact through gravity, influencing each other's star-forming behavior. When galaxies collide, tidal forces compress gas and trigger starbursts. The antennae galaxies, a famous example, display spectacular regions of intense formation where clouds have been squeezed by the merger. Conversely, some interactions strip gas away, quenching star formation and leaving behind quiescent remnants. The balance between these effects shapes the diversity of galaxies we observe. Spirals alive with birth, ellipticals resting in starlight, irregulars caught between chaos and renewal. The physics governing these cosmic processes remains consistent, from the smallest cluster to the largest galactic system. At its core lies the competition between gravity, which gathers matter, and energy feedback, which disperses it. This balance determines not only how many stars form but also how galaxies evolve. Computer simulations of galaxy formation, run on supercomputers with billions of particles, attempt to capture this interplay. They reveal that star formation is a self-regulated process. Too much activity increases feedback, which reduces gas density and slows formation, establishing a natural equilibrium over time. The connection between star formation and cosmic structure extends even further. The distribution of galaxies across the universe follows a web-like pattern, the cosmic web, defined by filaments of dark matter and gas. Within these filaments, gravity channels material toward nodes where galaxies form. Star formation within galaxies thus reflects the larger architecture of the universe itself. As gas flows along the filaments, it fuels new generations of stars, while outflows return enriched material to intergalactic space. This continuous circulation ties the life of individual stars to the evolution of the cosmos. Even within this vast context, the local details remain exquisite. Each star cluster, each glowing nebula, represents a single expression of universal laws. The interplay of turbulence, radiation, and magnetism produces structures of breathtaking beauty. Rippled edges, luminous arcs, pillars of gas that seem to defy gravity. JWST's images of regions like NGC 3324, known as the Cosmic Cliffs, capture these scenes in unprecedented detail, revealing the erosion of dense ridges by stellar radiation and the emergence of young stars along the fronts. These images are not only aesthetic, they are scientific data, encoding the conditions under which stars are born. The energy output from massive stars sculpts the surrounding gas into cavities and shells. As the gas cools, it can fragment into smaller clumps, leading to secondary generations of stars. Over millions of years, a single molecular cloud may host multiple cycles of formation and feedback, gradually dispersing while enriching the environment. The remnants of these cycles become part of the diffuse interstellar medium, from which new clouds will eventually condense. This continuous recycling maintains the galaxy's vitality, ensuring that the starlight we see tonight is part of an unbroken chain stretching back to the dawn of time. To the human eye, star formation appears timeless, but it is part of an evolving cosmic rhythm. The rate at which stars form in the Milky Way today is lower than in its youth, yet steady enough to sustain its glow. In regions like the Sagittarius Arm, massive star-forming complexes continue to shape the night sky, their radiation visible as bright knots of emission. Each newborn star adds a fraction of light to the collective brilliance of the galaxy, a reminder that creation is never truly still. As the cluster ages, the interplay between its members evolves. Stellar winds carve bubbles, ultraviolet light ionizes gas, and supernovae inject turbulence into the remaining material. The gas content diminishes, leaving a gravitationally bound system of stars. Some clusters remain dense and compact, surviving for billions of years as globular clusters. Others disperse, their stars mixing into the galactic field. These processes transform the distribution of mass and momentum within the galaxy, subtly influencing its long-term dynamics. Through this lens, star formation becomes not an isolated event but part of a continuum, a feedback-driven cycle linking birth, evolution, and death. Each stage prepares the conditions for the next, maintaining the balance of energy and matter that defines galaxies. Observations of external galaxies across cosmic time confirm this continuity. the same physics that governs a collapsing cloud in Orion also shapes the luminous cores of galaxies billions of light years away. The scale changes, but the principles endure. As our understanding deepens, so too does our appreciation for the subtlety of the universe. Star formation is not merely the consequence of gravity acting on gas. It is the expression of a finely tuned network of processes: cooling, chemistry, magnetism, feedback, all interacting across scales. The precision with which these factors align to produce stable stars and habitable worlds is a source of profound wonder. Every point of light in the night sky is evidence of this balance, a testament to the harmony inherent in physical law. In this quiet awareness, the observer finds peace. The immense distances, the slow unfolding of time, the steady glow of countless suns, all converge into a feeling of continuity and calm. To know the science behind the stars is not to diminish their beauty but to deepen it. The equations that describe collapse and fusion are, in their own way, lullabies of order and inevitability. They tell us that even in the vastness of space, there is coherence. Even in darkness, there is a patient emergence of light. As this section draws to a close, the view widens further. Beyond individual clusters and galaxies, the universe itself has been forming stars since its earliest epochs. The next part of this narrative will follow that story outward, to the cosmic scale of star formation through time, from the first stars that illuminated the darkness to the ongoing creation we witness today, guided by the same physical principles that govern every newborn sun. In the beginning, before any stars existed, the universe was dark and nearly uniform. For hundreds of millions of years after the Big Bang, the cosmos consisted primarily of hydrogen, helium, and traces of lithium, spread thinly across an expanding, cooling space. There were no heavy elements, no dust grains, and no galaxies, only a cosmic fog through which faint ripples of density moved, the seeds of future structure laid down by quantum fluctuations during inflation. The radiation that filled space gradually lost energy, shifting into the microwave band, leaving matter to dominate the universe's evolution. Gravity began to gather gas into the first halos of dark matter, silent and invisible scaffolds that would soon give birth to light. Within these dark matter halos, gas cooled slowly, guided only by the limited mechanisms available in a metal-free environment. Without carbon or oxygen, the only coolant was molecular hydrogen, which could form through rare collisions between protons and electrons. This process was inefficient, so the first clouds to collapse were massive, thousands of times larger than the ones forming stars today. As they cooled, they fragmented into a few enormous protostars cores, each destined to become a titanic star. These were the population 3 stars, the first generation to ignite in the cosmic dawn. Population 3 stars were likely far more massive than most stars we see now, perhaps 100 to several hundred times the mass of the Sun. Their immense gravity compressed their cores to extraordinary temperatures, triggering nuclear fusion at furious rates. They shone with ultraviolet light so intense that it began to ionize the surrounding hydrogen, carving expanding spheres of plasma in the primordial gas. Yet their lives were brief, mere millions of years, before ending in violent supernovae or, for the largest, complete collapse into black holes. In those explosions lay the beginning of chemical diversity. The first oxygen, carbon, silicon, and iron were forged and scattered, enriching the intergalactic medium. With each generation of massive stars, the composition of the universe changed. Tiny amounts of heavy elements acted as new cooling agents, enabling gas to condense more efficiently and fragment into smaller clumps. This marked the transition from population 3 to population 2 stars, still metal-poor, but no longer primordial. These new stars formed within nascent galaxies, the earliest recognizable systems in the universe. Their radiation began to pierce the cosmic fog, initiating an epoch known as rionization, when the intergalactic hydrogen became transparent to light. This process, occurring between about 400 million and 1 billion years after the Big Bang, transformed the cosmos from darkness to a web of luminous structure. Modern telescopes like JWST now peer into this era, capturing galaxies whose light has traveled for more than 13 billion years. Their images reveal compact, clumpy systems dominated by intense star formation, far denser than contemporary galaxies. Spectra from these objects show signs of extremely low metallicity, consistent with second-generation stars forming in environments barely enriched by the first. In some cases, the ultraviolet glow suggests the presence of extraordinarily hot, possibly massive stars, potential descendants of the population 3 era. Though direct detection of a truly primordial star remains elusive, these observations bring us closer to witnessing the first moments of starlight. Simulations of early structure formation help interpret these discoveries. In computer models, dark matter halos form hierarchically, merging to create larger systems. Gas falls along filaments into these halos, cooling and forming stars in bursts. Feedback from the first supernovae expels gas into surrounding space, temporarily halting star formation before gravity draws it back. This cycle of collapse, feedback, and accretion produces the patchwork pattern of early galaxies, small, bright, and short-lived. Over hundreds of millions of years, these building blocks merged to form the first substantial galaxies, precursors of the spirals and ellipticals we see today. The earliest black holes likely formed alongside these first stars. When a massive population 3 star collapsed, it left behind a black hole of tens to hundreds of solar masses. If located in a dense environment, such an object could rapidly accrete gas, growing into an intermediate mass black hole. Over cosmic time, such seeds might have evolved into the supermassive black holes now found at the centers of galaxies. The connection between early star formation and black hole growth is therefore fundamental. Both processes depend on the same gravitational wells and feedback mechanisms, and each influences the other's evolution. As enrichment continued, dust began to form. Tiny grains of carbon and silicate condensed in the ejecta of supernovae, mixing into the interstellar medium. These grains played a transformative role, enabling more efficient molecular formation and shielding gas from ultraviolet radiation. The presence of dust also changed the appearance of young galaxies, absorbing ultraviolet light and re-emitting it in the infrared. Observations with ALMA detect these signatures even in galaxies less than 1 billion years old, implying that dust production occurred surprisingly quickly after the first stars. Each grain, microscopic yet durable, became a carrier of cosmic history, the residue of ancient stellar death repurposed for new creation. Gradually, the pattern of star formation expanded from isolated halos to organized galaxies. The earliest galaxies were small, irregular collections of gas and stars, but through mergers and accretion, they grew more massive and structured. Spiral patterns and bulges began to emerge, guided by angular momentum and feedback. The rate of star formation increased dramatically, reaching its cosmic peak around 10 billion years ago. During that epoch, sometimes called cosmic noon, galaxies converted gas into stars at a rate hundreds of times higher than today. The universe glowed with ultraviolet radiation, its filaments alive with birth and energy. The conditions during cosmic noon differ from the calm star-forming regions we observe locally. In those early galaxies, gas densities were extreme, and turbulence was intense. Star formation occurred in vast clumps, each containing millions of solar masses of gas. Stellar feedback drove winds that blew material out into the circumgalactic medium, while accretion from the intergalactic web replenished it. This constant exchange maintained the high rate of activity for billions of years. The interplay of inflow and outflow, sometimes called the Baryon cycle, regulated galaxies' growth and chemical evolution. Even as the cosmic star formation rate peaked, individual regions within galaxies followed the same fundamental laws. The Kennickett-Schmidt relation, linking gas density to star formation rate, appears to hold across scales and epochs. This universality suggests that the underlying physics, gravitational collapse moderated by turbulence and feedback, remains unchanged. What differs are the environmental parameters: temperature, pressure, metallicity, and the availability of molecular gas. In high-redshift galaxies, these factors combine to accelerate formation, producing brilliant but short-lived systems that fade as their gas is consumed or expelled. The Ryanization of the universe, completed roughly 1 billion years after the Big Bang, was both a product and a driver of star formation. As young galaxies emitted ionizing photons, they created expanding bubbles of ionized hydrogen. Over time, these bubbles overlapped, transforming the intergalactic medium into a transparent state. The exact timing and contributors to this transition remain active topics of research. JWST's deep field observations aim to quantify the faintest galaxies responsible, while 21-centimeter radio surveys attempt to map the neutral hydrogen that remains. Together, these efforts are constructing the first detailed picture of how starlight reshaped the universe. Within this framework, the emergence of the first heavy elements had profound implications for future evolution. The metallicity of a gas cloud determines its ability to cool and fragment, setting the characteristic masses of the stars it forms. In the earliest epochs, cooling was limited, leading to massive stars. As enrichment progressed, smaller, longer-lived stars became more common. This transition laid the foundation for the diversity of stellar populations observed today. It also enabled the formation of rocky planets, since elements like silicon, magnesium, and iron are essential for solid surfaces. In a sense, the first stars not only illuminated the universe but also sowed the material necessary for life. Observations of extremely metal-poor stars in the Milky Way provide direct evidence of these ancient processes. Some halo stars contain less than 100,000th the Sun's iron content, yet show enhanced carbon or magnesium, signatures of specific nucleosynthetic pathways. By comparing their abundance patterns to theoretical yields from population 3 supernovae, astronomers can infer the properties of the first stars. These relics, scattered throughout the halo, act as time capsules preserving the chemistry of the early cosmos. Each spectrum reveals a story billions of years old, linking our galaxy to its primordial ancestors. The study of cosmic star formation across time relies on multiple observational traces. Ultraviolet light reveals young, massive stars. Infrared emission traces dust-obscured regions, and radio lines such as carbon monoxide and ionized carbon map the cold molecular gas. Combining these data yields a global star formation history, a curve showing how the average rate per unit volume of the universe has changed. It rises steeply from the dawn of galaxies, peaks around 10 billion years ago, then declines gradually to the present. This decline reflects both the depletion of gas and the heating of the intergalactic medium, marking the universe's gradual aging. Despite this downward trend, the process itself remains continuous. Even now, small galaxies continue to form stars in relative isolation. In the local group, systems like the Small Magellanic Cloud and IC 1613 exhibit ongoing activity, driven by their remaining gas supplies. Within the Milky Way, molecular clouds persist in the spiral arms, birthing new generations of stars and planets. The same laws that governed the first luminous objects still apply, ensuring that the universe, though older and quieter, remains a place of creation. Through the lens of modern astrophysics, we see the early universe not as a static beginning but as a dynamic sequence of transitions, from simplicity to complexity, from darkness to light. Each stage of star formation built upon the previous, adding new ingredients and new possibilities. The first stars established the chemical foundations, subsequent generations assembled the galactic structures, and within those, planets and life eventually emerged. In tracing this story, we recognize that the light we see in the night sky carries not just beauty but memory, the record of cosmic evolution written in photons. As we observe the faint glow from the most distant galaxies, we are witnessing the universe awakening. The photons that reach our telescopes today began their journey when the cosmos was young, traveling through expanding space for more than 13 billion years. Their arrival is a whisper from that ancient time, a signal that star formation has been shaping the universe almost since its birth. Each detection adds another thread to the tapestry, revealing the continuity that binds all epochs together. In this quiet understanding, the grandeur of cosmic history becomes something serene. The same physics that governs a newborn star in a nebula today once governed the first stars that ended the cosmic dark age. Across unimaginable time spans, the universe follows its own rhythm of creation, a slow breathing of light and matter. To contemplate it is to feel the scale of existence, vast, ordered, and enduring. As the universe matured, star formation did not cease. It evolved into a more balanced and intricate process. After the intense epoch of cosmic noon, when galaxies blazed with youthful vigor, the pace of creation began to slow. Gas supplies dwindled, temperatures rose, and the great furnaces of stellar birth settled into quieter rhythms. Yet even in this gentler phase, the formation of stars remained one of the most fundamental activities shaping the cosmos, a process of continual renewal that defines the character of galaxies. Within a typical spiral galaxy like the Milky Way, star formation occurs primarily in its thin disk, where cold molecular gas is concentrated. The interstellar medium is not uniform. It is a complex, multi-phase environment consisting of hot ionized plasma, warm neutral gas, and cold molecular clouds. Only the densest and coldest of these regions can collapse under gravity to form stars. In the Milky Way, such molecular clouds trace the spiral arms, their distribution revealed by observations of carbon monoxide emission at millimeter wavelengths. These clouds contain the raw material of creation, hydrogen molecules bound by gravity and shielded by dust. The rate of star formation in the Milky Way is estimated to be about 1 or 2 solar masses per year. This may seem modest, but over cosmic timescales it sustains the galaxy's brightness and diversity. Most of this activity occurs in giant molecular clouds spanning tens of parsecs and containing thousands of solar masses of gas. Within these clouds, dense clumps form cores that collapse to protostars, following the same physical principles that governed star formation since the dawn of time. Despite the galaxy's age and complexity, the laws remain unchanged. Gravity gathers, turbulence resists, and radiative feedback regulates. The Milky Way's structure plays an essential role in organizing this process. The spiral arms act as sites of compression, where density waves slow gas and increase its pressure. As clouds enter the arms, they collapse more readily, giving rise to bright H2 regions and young clusters. Observations of regions like the Carina Nebula and the Cygnus X complex reveal the vivid interplay between gas dynamics and radiation, captured beautifully by the Hubble Space Telescope and, more recently, by JWST. These star-forming regions shine in infrared light, where dust obscuration gives way to the glow of warm molecules and embedded stars. At the center of the Milky Way lies a contrasting environment. The galactic nucleus, surrounding the supermassive black hole known as Sagittarius A*, contains dense gas and strong tidal forces. Here, conditions are extreme. Temperatures are higher, turbulence is greater, and magnetic fields are stronger than in the disk. Yet even in this chaotic setting, stars are born. Observations with ALMA have detected compact molecular clouds and young stellar objects near the galactic center, suggesting that star formation can persist even under the influence of intense gravitational and radiative energy. The resilience of this process illustrates its adaptability across cosmic environments. Beyond the Milky Way, galaxies display an extraordinary range of star-forming behavior. Some, like the nearby Andromeda galaxy, are relatively quiescent, forming only a fraction of a solar mass of stars per year. Others, like the starburst galaxy M82, convert gas into stars 100 times faster. Starburst activity often arises from gravitational interactions or mergers, which drive gas into the central regions, increasing density and triggering intense formation. The result is a brief but brilliant phase, lasting tens of millions of years, in which the galaxy radiates far more energy than during its calmer life. Once the fuel is exhausted or expelled, the galaxy returns to quietude. Galaxies that form stars steadily rather than explosively follow a sequence often called the main sequence of star-forming galaxies. On a plot of stellar mass versus star formation rate, they lie along a relatively tight correlation, implying that most galaxies regulate their activity naturally. Too much star formation leads to feedback, stellar winds, supernovae, and radiation that expel gas or heat it, reducing efficiency. Too little, and gravity slowly draws gas back into denser regions. This self-regulation, evident across cosmic epochs, ensures a balance between creation and rest, allowing galaxies to evolve gradually over billions of years. Another key factor shaping star formation is environment. In dense galaxy clusters, the hot intracluster medium can strip gas from member galaxies, a process called Ram pressure stripping. As a galaxy moves through this medium, its interstellar gas is swept away, quenching star formation and transforming the system into a passive elliptical. In contrast, galaxies in more isolated regions retain the gas longer, sustaining star formation for extended periods. Observations of galaxy clusters like Virgo and Coma show this environmental diversity vividly. Spirals with truncated gas disks near the center, and vigorous star formation in the outskirts. The role of active galactic nuclei, or AGN, adds another layer of complexity. Powered by accretion onto supermassive black holes, AGN release enormous energy in the form of radiation and relativistic jets. This feedback can either suppress or trigger star formation. When powerful outflows expel gas, star formation halts. When shock waves compress surrounding material, it can ignite new birth. The balance between these effects is subtle and likely evolves over time. Simulations suggest that AGN feedback is a crucial mechanism in regulating galaxy growth, preventing excessive accumulation of mass and maintaining the observed diversity of galactic forms. As galaxies age, their ability to form stars depends on their gas content and metallicity. Observations show that star formation efficiency, the rate at which gas converts to stars, correlates with molecular gas fraction and pressure. Metal-rich environments tend to cool more effectively, promoting molecular formation, while low metallicity galaxies may retain large amounts of atomic gas without active star formation. The Small Magellanic Cloud, for example, contains abundant gas but relatively low star formation efficiency, illustrating how chemical composition shapes galactic behavior. In elliptical galaxies, the story differs. Most ellipticals formed their stars rapidly in the distant past, during massive bursts triggered by mergers. Their gas was then consumed or expelled, leaving them dominated by old, red stars and hot, X-ray emitting gas. Yet even these seemingly dormant systems can harbor pockets of renewal. Deep observations reveal small amounts of cold gas and occasional star-forming regions, often linked to cooling flows or minor mergers. The universe's creativity persists, even in places that appear still. The evolution of star formation on the cosmic scale mirrors the life of an individual galaxy. After the peak at cosmic noon, the average rate declines steadily. The mechanisms driving this slowdown include gas exhaustion, feedback, and the gradual reduction of inflow from the intergalactic medium. As galaxies grew more massive, their halos heated the infalling gas, preventing it from cooling efficiently, a phenomenon known as virial shock heating. Over time, this reduced the supply of cold gas available for new stars, ushering in a more quiescent cosmic era. Despite this general trend, the universe continues to display remarkable pockets of vitality. Dwarf galaxies, though small, remain prolific star formers relative to their mass. Their shallow gravitational potentials make them sensitive to feedback, causing bursts of activity followed by periods of rest. This bursty behavior contributes to their irregular shapes and diverse appearances. Observations of nearby dwarfs, such as NGC 1569 and Sextans A, show clusters of young stars and expanding shells of gas, evidence of recent formation. These systems demonstrate that even on the smallest scales, the rhythm of creation continues. In the broader cosmic web, star formation traces the flow of matter through filaments and nodes. Gas accretes along these structures, feeding galaxies and groups. Observations of circumgalactic gas using quasar absorption lines reveal that much of the universe's baryonic matter resides not in stars, but in diffuse, ionized halos surrounding galaxies. This gas acts as both reservoir and regulator, supplying material for future formation while responding to the feedback from ongoing processes. The circulation of matter between galaxies and their surroundings sustains the universe's slow evolution toward equilibrium. Modern instruments have transformed our view of these processes. The Atacama Large Millimeter, Submillimeter Array provides exquisite detail of cold gas and dust, resolving the structure of molecular clouds in nearby galaxies. JWST extends this vision into the infrared, unveiling star formation obscured by dust. Together, they reveal the universality of the process. In all environments, stars form from the same basic ingredients and under the same physical laws. Whether in a quiet spiral arm or a turbulent merger, gravity, cooling, and feedback work in concert to produce light. The study of star formation in the mature universe also informs our understanding of cosmic ecology. The conversion of gas into stars not only creates new light but also drives chemical evolution. Each generation enriches the interstellar medium with heavier elements, altering the cooling properties of subsequent clouds. Over billions of years, this gradual enrichment leads to the variety of compositions observed in stars today. From this diversity arises the potential for planets and, eventually, life. In that sense, the ongoing rhythm of star formation is the mechanism by which the universe becomes more complex. Within our own galaxy, future generations of stars are already being prepared. In the Orion complex, massive clouds like L1641 continue to fragment, producing clusters of young stellar objects. In the far outer disk, smaller, quieter clouds form stars more slowly, preserving gas for billions of years to come. The Milky Way's reservoir is not infinite, but it is ample enough to sustain formation for another 10 billion years, barring major disruption. Our galaxy, like others, lives within the balance of consumption and renewal, a cosmic heartbeat measured in eons. As we look outward, we see galaxies at every stage of this continuum. Some still blaze with youth, others drift into calm maturity, and a few rest in near silence. This variety, captured in deep surveys, reflects the stochastic nature of cosmic evolution. Yet beneath the diversity lies unity. The same physics, the same processes, the same delicate equilibrium that has guided creation since the first stars ignited. It is a universe of immense scale, yet governed by simple, universal laws. Over time, star formation will continue to decline. As galaxies consume their remaining gas, the cosmos will grow dimmer. The current era, rich with starlight, will eventually give way to one dominated by red dwarfs and fading remnants. But this transition will unfold over trillions of years, far beyond the span of human or even planetary existence. For now, the universe is still luminous, still vibrant with creation. Every night sky is evidence of ongoing activity. Each point of light a moment in the continuous unfolding of cosmic history. In reflecting upon this, one finds tranquility. The realization that even amid vast time and distance, The universe maintains its balance, neither rushing nor halting, but evolving with quiet persistence. The glow of galaxies across the deep field is not static. It is the visible trace of processes still underway, as gravity and energy weave their enduring interplay. To study star formation is to glimpse the mechanics of eternity, a slow, deliberate dance of matter into light. As stars age within the calm arms of their galaxies, they transform the raw material of the universe into something richer and more intricate. What began as cold hydrogen has become luminous plasma. What began as darkness now radiates across light years. Every atom within a star participates in the grand experiment of thermonuclear equilibrium, a balancing act between gravity's pull inward and radiation's pressure outward. This equilibrium defines a star's long middle age, the main sequence, where most of its life quietly unfolds. Inside the stellar core, hydrogen nuclei continue to merge into helium through fusion chains, predominantly the proton-proton cycle in small stars like the Sun, and the carbon-nitrogen-oxygen cycle in larger, hotter ones. These reactions convert mass into energy with stunning efficiency. A tiny fraction of matter transformed into vast amounts of radiant power, following Einstein's simple but profound equation, E = mc squared. The energy moves outward through layers of plasma, first by radiation, then by convection, until it escapes from the photosphere as light. That light is what warms planets, drives chemistry, and sustains life. But from the cosmic perspective, it is also feedback, energy returned to the galaxy's interstellar medium. Stellar radiation, winds, and later supernovae regulate the temperature, pressure, and chemical state of surrounding gas clouds. Thus, each generation of stars prepares the stage for the next. The galaxy becomes a living network of exchange, its luminous nodes bound by gravity and replenished by stellar death. In regions still dense with gas, this radiation sculpts the next generation of stars. Astronomers call this process sequential star formation. When ultraviolet light from massive, short-lived stars strikes a nearby molecular cloud, it compresses the gas at the surface, forming bright ridges called ionization fronts. Over time, these fronts trigger collapse deeper within the cloud, giving birth to new protostars. The phenomenon is visible in structures like the Carina Nebula, where JWST imagery shows cavities carved by radiation pressure and, along their rims, small globules dense enough to ignite. The cycle is perpetual. Energy from one generation becomes the catalyst for the next. Stars also migrate. Clusters gradually disperse as gravitational interactions fling members outward. Some drift alone through the spiral arms, others remain loosely bound as associations. Our own Sun likely formed in such a cluster about 4.6 billion years ago, in a region enriched by earlier supernovae. The presence of short-lived isotopes in meteorites, such as aluminum-26, suggests that a nearby massive star exploded just before the solar system formed, seeding the nebula with heavy elements. Thus, even in our origin story, the death of one star contributed to the birth of another. This enrichment process is the galaxy's slow alchemy. Within stellar cores, successive generations forge heavier elements: carbon, oxygen, nitrogen, silicon, iron. When stars die, through winds or supernovae, these elements return to space, joining new clouds that will eventually collapse again. Over billions of years, the interstellar medium becomes chemically evolved. The first stars, formed only from hydrogen and helium, produced none of the materials necessary for life. But their descendants, through countless cycles of fusion and dispersal, have filled galaxies with the ingredients of planets, oceans, and living cells. In the quiet light of modern observatories, we can now trace this enrichment in exquisite detail. The JWST spectroscopic instruments detect specific absorption lines corresponding to complex molecules, water, carbon monoxide, even simple organics, in young disks. ALMA reveals how dust grains coated with ices begin to clump and grow. The building blocks of planets, and possibly of biochemistry, are present almost from the earliest stages of stellar birth. When astronomers look toward distant galaxies, they see that this process repeats everywhere, following the same physical laws but unfolding at different tempos. In starburst galaxies, where collisions compress gas, the rate of star formation can be hundreds of times higher than in the Milky Way. In more quiescent galaxies, it slows to a gentle drift of creation. Yet the pattern remains. Clouds collapse, stars ignite, and radiation shapes the next cycle. The universe is self-similar, scaling the same physics from small clusters to vast galactic networks. The cosmic star formation rate itself has a history. Observations show that it peaked about 10 billion years ago, during what astronomers call cosmic noon. At that time, galaxies were rich in gas and full of youthful vigor, forming stars at extraordinary rates. Since then, the supply of cold gas has gradually diminished. Modern galaxies, including ours, form stars more slowly, though the process continues wherever molecular clouds remain dense. Even as the overall pace declines, the universe remains luminous, sustained by countless ongoing births. Understanding why the star formation rate changes requires studying the flow of matter on intergalactic scales. Galaxies grow by accreting gas from their surroundings, cold streams drawn along cosmic filaments of dark matter. This inflow replenishes the interstellar medium, while stellar feedback and supernovae drive outflows that expel material into galactic halos. The delicate balance between inflow and outflow determines how long a galaxy can sustain star formation. Modern simulations, such as the Illustris TNG and FIRE projects, model these exchanges across billions of light years, showing how large-scale structure and small-scale physics intertwine. Each star, regardless of its size, participates in this balance. Massive stars dominate feedback, enriching and stirring the medium. Smaller ones preserve it, shining steadily over cosmic time. Red dwarfs, though faint, are the silent majority, ensuring that the galaxy never truly goes dark. Their lifespans exceed the current age of the universe by orders of magnitude, meaning none have yet reached old age. They are the keepers of the long future, tiny furnaces that will still glow when all massive stars are gone. Amid this vast network of processes, our understanding continues to evolve. New instruments map magnetic fields in unprecedented detail, revealing how they thread through clouds and influence collapse. Observations of polarized light from dust grains show that magnetism neither fully halts nor fully dominates star formation. Instead, it acts as a guiding tension, channeling material along preferred directions. The result is a universe shaped by a dialogue between order and turbulence, structured yet spontaneous. In the tranquil flow of time, galaxies breathe through this interplay. They are not static collections of stars but dynamic ecosystems, constantly renewing themselves. Each photon emitted by a young star carries information about the conditions that produced it, traveling through space for eons until it reaches our telescopes. When we capture that light, we glimpse both the present and the ancient past, a continuum of creation stretching back nearly to the dawn of time. To contemplate this cycle is to realize that the cosmos is not a place of isolated events but of interwoven processes. Every molecule of oxygen in our lungs, every atom of carbon in our bodies, once resided in the heart of a star. The same gravitational laws that shaped the earliest protostars continue to shape us, holding us within the fabric of the Milky Way. The connection is not poetic invention but physical truth, measurable in spectra and isotopic ratios. As Part 5a draws its calm breath, we linger within this awareness that the birth of stars is not merely a chapter in cosmic history but the mechanism through which the universe renews itself. Each star, from the faintest red dwarf to the brightest giant, is both outcome and origin. Its light carries forward the story of everything that has ever been, illuminating the darkness not through chaos but through patient order. Beyond this point, the narrative will drift toward reflection. How these stellar processes shape galaxies, and how the ongoing rhythm of formation and decay defines the fate of the cosmos itself. The science will remain clear, yet the tone will soften, allowing the listener to drift deeper into rest, carried by the quiet certainty that the same physics guiding the stars also guides the silence between them. The galaxy breathes in light and exhales darkness, a continuous rhythm of creation and dispersal. When we look up at the night sky, what we see is only a thin slice of this rhythm, stars at many stages of their lives, scattered like embers across an immense cosmic tapestry. Each point of light marks a different phase in a cycle that has persisted for more than 13 billion years. To study star formation is to trace that cycle from beginning to renewal, to see the physics of matter transfigured into energy and back again. In the quiet spiral arms of the Milky Way, gas clouds still gather, though more slowly than in the galaxy's youth. The central regions pulse with waves of density that move outward like ripples, compressing clouds along the way. These spiral density waves act as galactic traffic jams, slowing material just enough for gravity to take hold. Modern surveys, such as the Gaia mission combined with ALMA maps, reveal how these waves organize star-forming regions into chains of nurseries. Each bright cluster along an arm is a trace of where the wave has passed. Star formation is never evenly distributed. It depends on metallicity, magnetic fields, and feedback from earlier generations. In the outer galaxy, where heavy elements are scarcer, the cooling of gas is less efficient, and clouds collapse more reluctantly. Closer to the core, enrichment and turbulence make the process more vigorous. Observations from the Atacama Pathfinder and JWST confirm this gradient. The chemistry of a star-forming region subtly changes with galactic radius, influencing both the kinds of stars that form and the potential for planetary systems around them. The link between environment and outcome is becoming clearer through long-term surveys. Instruments like Vera in Japan measure the motions of masers, natural microwave beacons in star-forming regions, with exquisite precision. From these data, astronomers map the Milky Way's spiral structure in 3 dimensions. They find that the arms are not fixed but transient, winding and unwinding over hundreds of millions of years. As they shift, they shepherd gas into new configurations, ensuring that the process of star birth never completely ceases. On smaller scales, the formation of clusters follows the same logic. Gas fragments hierarchically. Large clouds break into filaments, filaments into cores, and cores into multiple systems. The result is often a stellar nursery where dozens of young stars interact gravitationally. Some binaries remain bound for life, others are ejected, becoming the solitary travelers that populate the field. Computer simulations run on petascale machines trace these interactions particle by particle, revealing that most stars experience close encounters early on, exchanges of angular momentum that can tilt disks and influence planet formation later. Even as we model these details, new discoveries refine the picture. JWST's observations of the Orion Bar show that photodissociation regions, where intense ultraviolet light breaks apart molecules, are far more complex than expected. Layers of ionized, atomic, and molecular gas interleave like pages of a cosmic book. Each layer hosts different chemical reactions, gradually building the diversity of molecules that will be incorporated into future systems. This layering explains why infrared spectra from star-forming clouds contain so many distinct features. The universe is running countless experiments in chemistry simultaneously. As stars mature, their feedback becomes both sculptor and destroyer. Stellar winds sweep cavities, radiation compresses some areas and disperses others. The Carina Nebula, for example, shows networks of pillars and arcs where this feedback has carved exquisite detail. In JWST's high-resolution imagery, astronomers can now measure how shock fronts move through the gas, watching the propagation of energy in real time. These measurements tie directly into models of galactic evolution. The same feedback that clears a small nebula scales up to regulate entire galaxies. In the broadest view, the interplay between star formation and galactic structure dictates the universe's luminous history. Surveys of deep space, such as the Hubble Ultra Deep Field and Webb's CERS program, trace how galaxies evolved from clumpy, irregular systems into the grand spirals and ellipticals we see today. In those early epochs, star formation was more chaotic, influenced by frequent mergers and abundant gas. Over time, as heavy elements accumulated and feedback intensified, galaxies settled into steadier rhythms. The laws did not change, only the balance of forces did. Every observation reminds astronomers how intertwined scales are. A single magnetic filament within a cloud influences the arrangement of stars in a cluster. The sum of thousands of clusters shapes the brightness of a galaxy. Billions of galaxies determine the glow of the cosmos. The same equations, hydrodynamics, radiation transfer, gravity, apply from parsecs to megaparsecs. It is this consistency that gives astrophysics its quiet beauty, the realization that the entire visible universe operates on variations of a single theme. In the midst of this structure, turbulence plays its paradoxical role. It both supports and seeds collapse, stirring the gas with vortices that create localized density peaks. Theories of supersonic turbulence describe how energy cascades from large scales down to tiny eddies, much like weather in Earth's atmosphere. Yet in interstellar space, these eddies span light years. Radio observations of carbon monoxide emission lines reveal these motions directly, their Doppler shifts mapping velocity fields across entire clouds. From this data, scientists derive statistical relationships, like Larson's laws, that tie together cloud size, velocity dispersion, and density. Even the chaos follows order. As the data accumulates, astronomers refine the star formation efficiency, the fraction of a cloud's mass that becomes stars before feedback disperses the rest. On average, only about 1% of molecular gas converts into stars per free fall time. This inefficiency may seem modest, but it ensures longevity. Were the conversion faster, galaxies would have exhausted their gas long ago. Instead, the universe has tuned itself to a sustainable tempo, allowing light to emerge gradually over billions of years. In this long tempo lies the serenity of cosmic time. Human scales are fleeting. The processes that give rise to stars unfold across epochs beyond imagination. Yet instruments, algorithms, and patient observation allow us to perceive them. A sequence of infrared frames taken over decades can reveal jets changing shape. Spectral lines can show a protostar's accretion slowing. Through data, we witness what would otherwise seem motionless. The cosmos whispers its transformations in wavelengths instead of words. And so, the story of star formation extends naturally into the story of observation, the dialogue between what happens and what can be known. The photons that left a forming cluster thousands of years ago reach our telescopes tonight, carrying with them signatures of density, temperature, and composition. To interpret them is to reconstruct the conditions of distant nurseries. Every spectrum is a kind of memory, a record of energy exchanged between gravity and gas. As we listen to these distant memories, the universe seems less remote. The same atomic transitions that create light in a protostar's core occur in laboratories on Earth. The same forces shaping a nebula operate within our planet's gravity. The difference is scale, not substance. This continuity connects everything, from the subtlest vibration of hydrogen molecules to the architecture of galaxies. In understanding star formation, we are not merely cataloging distant phenomena, we are tracing the logic of matter itself. With this awareness, the narrative begins to quiet again. The engines of fusion continue unseen, steady as breath. Around them, clouds cool, fragments drift apart, and the cycle prepares to repeat. There is no final act, only continuation. a symmetry between collapse and expansion, darkness and light. The physics that governs it is indifferent yet elegant, producing beauty not by intention but by inevitability. In the faint silence of interstellar space, the story of stars reaches a slower, deeper rhythm. Each point of light we see in the night sky represents a balance that has been achieved, a harmony between gravity and pressure, between contraction and radiation. But that balance, though stable for millions or billions of years, will not last forever. The processes that form stars eventually bring them to their end, and those endings feed new beginnings in an unbroken sequence that defines the luminous history of the cosmos. To understand the final arc of this cycle is to return to the physics that began it. A star forms when gravitational potential energy becomes thermal energy. It shines because nuclear fusion converts mass into light. Over time, as the internal hydrogen fuel diminishes, the equilibrium changes. In massive stars, that change is rapid and spectacular. In small stars, slow and nearly imperceptible. Each path contributes differently to the galaxy's future supply of gas and heavy elements, setting the stage for the next generation of formation. Massive stars live brief, radiant lives. They fuse hydrogen through the CNO cycle at millions of times the rate of our Sun. When hydrogen runs out, helium burning begins, followed by the successive fusion of heavier nuclei, carbon, neon, oxygen, silicon, until iron forms in the core. Fusion beyond iron is endothermic. It cannot sustain pressure against gravity. The core collapses, releasing gravitational energy in an instant. A supernova follows, hurling elements across interstellar space at thousands of kilometers per second. These ejecta enrich the surrounding medium with oxygen, calcium, and iron, the building blocks of planets and biology. Every rocky world owes its material to such explosions. Medium-mass stars, like the Sun, evolve more gently. They expand into red giants, shed their outer layers into glowing shells known as planetary nebulae, and leave behind white dwarfs, dense, cooling remnants supported by electron degeneracy pressure. Over time, these white dwarfs radiate their heat into space, fading into invisibility. The gentle winds, though modest compared to supernovae, also return carbon and nitrogen to the interstellar medium. In clusters, telescopes can trace this recycling directly. The gas expelled by one generation coalesces in the next, connecting epochs in a continuous chain. Low-mass stars, the ubiquitous red dwarfs that make up most of the Milky Way's stellar population, evolve on timescales longer than the current age of the universe. None have yet reached their final stages. They burn their hydrogen slowly and steadily, fusing every bit of fuel before eventually turning into dim white dwarfs. Because they are so numerous and long-lived, they act as a cosmic reservoir of light. Long after more massive stars have died, red dwarfs will continue to shine, keeping the universe faintly illuminated for trillions of years. These varied endings demonstrate why galaxies evolve in such diverse ways. A spiral like the Milky Way can sustain star formation for billions of years because its stellar deaths continually replenish its gas. In contrast, an elliptical galaxy, formed by mergers and intense early starbursts, can burn through its supply rapidly and then remain quiescent. Observations from the Sloan Digital Sky Survey and ALMA show that this quenching is driven both by gas exhaustion and by feedback from supermassive black holes. The same energy that powers quasars also prevents new stars from forming, a cosmic self-regulation. At larger scales, this self-regulation is evident in the cosmic star formation history. By measuring the brightness and redshift of distant galaxies, astronomers have reconstructed how the rate of star birth has changed over time. It peaked around 10 billion years ago, a period known as cosmic noon, when galaxies were rich in cold gas and interactions were frequent. Since then, the rate has declined steadily, falling by roughly an order of magnitude to its present level. The universe still forms stars, but more quietly now, with most activity confined to spiral arms and irregular dwarfs. The age of intense creation has given way to an age of gradual refinement. Even as the rate declines, the mechanisms remain universal. Whether in a dwarf galaxy a few thousand light-years across or a massive spiral spanning 100,000, the interplay between cooling, turbulence, and gravity dictates where stars appear. Data from JWST's surveys of early galaxies confirm that the same physics applied even within the first billion years after the Big Bang. Molecular clouds, filaments, and compact clusters already existed. The difference was density. Everything was closer together, richer in gas, and faster in evolution. In those early epochs, galaxies doubled their stellar mass in mere hundreds of millions of years. The early universe was, in essence, a continuous star-forming engine. Quasars illuminated its filaments, and the ionization of hydrogen began. Young, massive stars provided the ultraviolet light that transformed the neutral universe into an ionized one. Today, JWST has observed galaxies whose light left them only 300 million years after the Big Bang, revealing populations of stars far more massive and luminous than those common now. These first generations, known as Population 3, forged the earliest heavy elements and seeded the environments that would later produce Population 2 and Population I stars, including the Sun. Tracing this evolution from Population 3 to the present links cosmology to stellar astrophysics. The same gravitational instabilities that formed the first clouds are still at work, only on smaller, gentler scales. Computer models using cosmological hydrodynamics simulate this continuum, connecting the web-like structure of dark matter to the birthplaces of individual stars. In these simulations, dark matter forms the framework, baryonic gas flows along its filaments, and star formation ignites where density peaks occur. The universe's visible beauty is thus a luminous overlay on a deeper, invisible architecture. In this framework, star formation acts as both an outcome and an agent. It results from the gravitational assembly of matter, and it drives the thermal and chemical evolution of the universe. Without it, there would be no galaxies, no planets, no chemistry beyond hydrogen and helium. Every atom of carbon in living organisms was once processed in a stellar core. The calcium in bones, the iron in blood, the oxygen we breathe, all were created in the interiors or explosions of stars. The cycle of star formation is, in a literal sense, the origin of life's materials. The connection between stellar physics and biology underscores a profound continuity. The processes that unfold across trillions of kilometers ultimately determine the composition of cells on Earth. Yet nothing about the cosmos suggests design or intent. It is a consequence of physical law. The simplicity of hydrogen interacting through gravity and quantum mechanics gives rise to complexity without guidance. The symmetry of cause and effect stretches seamlessly from the collapse of gas clouds to the spark of life in a planetary ocean. Modern astrophysics, with its expanding reach, brings this realization into focus. JWST, ALMA, Gaia, and upcoming observatories like the Vera Rubin Telescope and the Nancy Grace Roman Space Telescope are building a continuous record of star formation across cosmic time. These data do not merely confirm theories, they reveal nuance. The shapes of nebulae, the chemistry of protoplanetary disks, the structure of stellar populations all speak to variations in environment and history. The story grows more intricate, but the underlying rhythm remains constant. In the far future, that rhythm will slow. As gas supplies diminish and feedback continues to heat the interstellar medium, galaxies will form fewer new stars. The brightest will fade first, leaving behind red dwarfs and long-lived remnants. Over trillions of years, even these will cool into black dwarfs, objects of almost perfect equilibrium, where no fusion remains. The universe will enter what physicists call the degenerate era, illuminated only by the faint residual glow of matter radiating its last stored energy. Eventually, on timescales so immense they challenge imagination, gravitational interactions may cause even those remnants to merge or evaporate. Black holes will dominate, slowly losing mass through Hawking radiation until they, too, disappear. The universe will become dark again, filled only with thin gas and the silent drift of elementary particles. Yet even this state will not erase the legacy of star formation, for every atom will bear the imprint of its stellar origin. To contemplate this distant outcome is not melancholy but serene. It is the natural conclusion of a process that has balanced itself for eons. The cosmos does not mourn its fading light, it follows the principles that gave it form. The story of stars is not one of permanence but of transformation, a vast, slow exchange between matter and energy. The light of every sunrise, the glow of every nebula, the shimmer of every galaxy is a brief moment in that continuum. For humanity, the study of star formation is both scientific and reflective. Through observation, we uncover the mechanisms of collapse and fusion, of turbulence and feedback. Through reflection, we recognize our place within those mechanisms. The atoms composing our thoughts were once dust grains in a stellar nursery, warmed by radiation, swept into disks, and eventually drawn into a forming planet. To understand star formation is, in a quiet way, to understand ourselves, as matter shaped by gravity and illuminated by time.